In May 2026, 30 prominent Bayesian machine learning researchers published a position paper at ICML. The title of the paper is Position: Agentic AI Orchestration Should be Bayes Consistent. Their central, uncompromising claim is that coherent decision-making requires Bayesian principles at the orchestration level. This chart shows the exact opposite happening in practice. A 2025 survey of 306 practitioners reveals 80% use hard-coded control flow and 0% use Bayesian primitives. Furthermore, 68% of deployed agents take 10 steps or fewer before human intervention. This creates an immediate engineering paradox. The most mathematically rigorous theoretical paper of the year dictates that builders must orchestrate agents using formal probability, yet the production data proves nobody is actually doing it. Engineering leaders are now forced into a corner. They have to decide whether to invest their team roadmaps into building these Bayesian primitives from scratch, or to ignore the academic consensus entirely. The reality is that neither the paper nor the practitioners are wrong. To resolve this contradiction, we have to look outside of machine learning entirely and examine historical software adoption patterns. This is Bearded AI Guy. I break down the architecture of AI agents based on the work of the human architect, designed specifically for builders who ignore the hype and focus on what actually ships. The historical analogy that perfectly explains the fate of this position paper is TypeScript. The software industry will absorb the pragmatic, productivity-enhancing fragments of Bayesian theory. At the same time, it will completely reject the computationally expensive mathematical purity required to implement it in full. To see why, we need to define the true Bayes-consistent orchestration model, construct a minimal implementation to see what it actually takes to run, and look at the evidence pointing to a TypeScript-like trajectory by 2028. Mapping this trajectory allows teams to identify which Bayesian primitives are ready for production and which are likely to remain theoretical curiosities for years to come. A large language model can sound entirely certain while generating text, yet be completely wrong about the actual task it is trying to accomplish. Predicting the next word successfully does not equal knowing the right action to take next. The system can have high confidence in its grammar while possessing zero confidence in its strategy. To fix this, we have to move past the informal idea of confidence and look at the formal separation of the prediction layer and the control layer. The paper's formal requirement is separating token uncertainty from decision uncertainty. A distinct control layer must maintain an explicit belief state. It has 4 strict requirements. First, it maintains a discrete belief state over a decision-relevant latent variable. Second, an observation model maps tool messages to likelihoods. Third, a belief update applies Bayes' rule. Fourth, an action rule driven by posterior expected utility determines routing or escalation. Token probabilities are mathematically insufficient to serve as a control state. Without these 4 explicit components, a system is just stringing together text. It is not orchestrating decisions. The simplest way to track tool reliability is to keep a running scorecard. When a tool succeeds, you increase its success score. When it fails, you increase its fail score. You then use that scorecard to make decisions. You look at the options and always pick the tool with the highest estimated value, subtracting the specific cost of running it. That simple concept is exactly what the authors endorse in Appendix C of the paper, using a structure known as a Bayesian bandit. Here's a technical implementation using Thompson sampling. Each tool gets a profile with beta distributed parameters, alpha for prior successes, beta for prior failures. The router pulls a sample from each posterior. It computes utility by multiplying success probability by success value, subtracting cost, and selecting the peak. If the peak falls below a threshold, it flags for human escalation. Running this requires rigorous engineering.
You need explicit priors, calculate real-time posterior updates after every observation, and maintain strict outcome-linked logging to feed the math. The primary hurdle for Bayes-consistent orchestration is the massive engineering tax of building labeled feedback loops, which often outweighs the complexity of the math itself. Not a single leading agent framework built today can accomplish what the paper demands right out of the box. LangGraph forces you to build math, Pydantic checks if data looks right, and Claude guesses the next step. To see exactly why this massive gap exists today, we have to look deeper at the underlying architecture of these modern frameworks. This matrix evaluates top frameworks against the paper's criteria. LangGraph has the correct topological shape with shared typed state, but 0 native probabilistic primitives. Pydantic AI excels at explicit dependency safety and output validation, but these are heuristic control hooks, not posterior inference primitives. The Claude agent SDT relies on a model-driven tool loop driven by token probabilities, failing all criteria. Right now, Bayes-consistent orchestration only exists as a massive custom architectural overlay. The chasm between academic correctness and mainstream tooling defaults is wide. There is a brutal economic truth in software architecture. Perfectly correct ideas only win if they are cheap to use. If a correctness framework requires a PhD to understand or demands endless maintenance to operate, developers will find a cheaper shortcut that is simply good enough. We can see this exact pattern play out across 3 historical case studies of correctness adoption: double-entry bookkeeping, formal verification, and TypeScript. 15th century double-entry bookkeeping achieved total adoption because its core invariant, balancing debits and credits, was computationally trivial. On the other extreme, formal verification models like Cell4 offer perfect correctness, but remain quarantined to high-stakes niches because the encoding cost is too high. TypeScript is the predictive analog. It explicitly rejected provable soundness for developer productivity, securing 50% adoption. The law of correctness adoption states that correctness wins when it is cheap to encode and expensive to ignore. Because full Bayes consistency is computationally expensive and difficult to validate, it is guaranteed to face a TypeScript-style compromise. The paper undeniably wins in theory. The distinction between token and decision uncertainty is a load-bearing architectural truth that the industry cannot unlearn. But the market undeniably wins in practice. Teams won't pay the strict engineering tax required for full expected utility maximization across every tool loop. The industry will standardize the weak form of the paper. Frameworks will absorb explicit task-level state tracking, calibrated confidence scores, outcome-labeled logging, and contextual bandit routers for basic tool selection. At the same time, the industry will categorically reject the strong form for standard use. You will not see mainstream frameworks requiring explicit priors over latent states, continuous posterior updates after every observation, or dependence-aware evidence pooling. The industry is going to struck the paper for its pragmatic parts. This will create agent frameworks that are less heuristic, but they will fall far short of a true Bayesian control loop. By 2028, at least one major agent framework will ship contextual bandits and calibrated routing as a first-class native feature. But no mainstream framework will ever require you to encode explicit prior and posterior math just to run a general-purpose agent loop. Correctness only wins when it is cheap to encode, easy to audit, and expensive to ignore. Agent loops are moving towards a TypeScript for Bayes model, a pragmatic compromise that prioritizes developer utility over mathematical perfection. Drop a comment with the specific heuristic shortcut in your current agent stack that you've been calling good enough. And if you want the expanded arguments from this 7-part series, check out the Human Architect's book, AI Agents in Action.